Oops. All right, here is another example for class number 11. I'm doing shaft example 654. Right, so in this one we have the 2,500 and the 1,000 pounds from problem 617, and they're applied here onto this. It's only it's a 2D shaft instead of a 3D shaft, really. But anyway, it's the same idea, except with just another additional plane. And now it has 2,500 pound foot, or excuse me, pound inch torque. And I also say, well, wait, what if it was 1,600 RPM? What would the horsepower be? It's a good thing to know. So working through this, first off, if we had 2,500 inch-pounds and it was 1,600 RPM, that would be 63.5 horsepower. I think this is an important type of thing to do in a problem in college, right? Learning mechanical engineering in college. So to start forming sort of a relative idea of what we're talking about, what piece of kind of equipment would have something that's 63.5. So you have something to compare to in the real world. That'd be a very sort of like a mini bike, like not a very powerful. Well, is that true? Let me think. I'm not thinking CCs. I'm sorry, I shouldn't think of it in CCs. Definitely, this would be like half a Honda Civic with a horsepower. So that'd be a pretty big motorcycle, I guess, but not like a big Harley one. It would. Well, I think that's probably the best equivalent I can think of in terms of like relative size of, because like a Honda would be like 100 to 120 horsepower, where this little itty, it's small but not too. Because of its lightweight, it could be fairly get some pretty good pickup. But anyway, that's what I would estimate as a comparison. So I'm lazy. So here's the shear moment diagram from the solution manual. Yes, you should definitely find these reactions yourself, and you can see that the reactions are 2,000 and 1,500 at this location A and location B. And the maximum might be this 16,000. But the spot we kind of would think that's probably most likely to fail is right there at that transition. So we could find the moment right there, that 14,750, and use that for our bending. Because first off, we could get our alternating and mid-range stresses, right? So the bending is completely reversed to 14,750 inch-pound moment is going to cause tension and compression in that full amount. And then the constant torque on this of 2,500 is going to also be applied. The stress concentrations we can look up. Did I put them up there? No, I guess we can take it on faith that we were able to find these from table 15.8 and 15.9 for this ratio of D over D and this fillet radius right in there, 1/16 apparently, compared to that diameter. And so 1.6, 1.95, and then use that 1/16 of an inch along with the ultimate strength in these figures 620 and 621 to find the notch sensitivity for both bending stress and shear stress, and then apply them to both of these and get the fatigue stress concentration, which is slightly less because of the notch sensitivity. So 1.72, 1.49. And now we can get these as stresses. And I'm including this equation here, but notably didn't really need to. It just noting how the math works out to the thing. We're squaring it and then taking the square root of it. So not 100% necessary to do that. What is necessary is this 3 over here. Like, we didn't have to write out this part of the equation, but it did. that 3 is going to definitely come into play. So you did need to do this math right here. You can't just ignore that square root, because you could have up here because it was squared and then it's square rooted. But anyway, so you can also see that this mid-range doesn't play a whole lot a part into here. And then when we go in and we take a look, okay, so first we have to take care of the material, which we could have done earlier. Is right here. So what is that? That's a 85 KSI, 1/2 of it for the SE prime. You get the surface factor, you get the size factor, and it's round and it's rotating, so you don't have to do the equivalent diameter. KC, because it's equal to 1. That's what we do with these equations. And we don't do anything with temperature reliability. We end up with an endurance strength of 29.5. And now we go to the safety factors. Langer says it's fine, but just barely. But remember, we're doing a little bit of a conservative approach right here. And then take a look at Goodman, and it definitely dies. Definitely is going to die. And you could really see that as part of like how large that endurance, the alternating is compared to the endurance strength. It was always going to fail. And the mid-range doesn't even play much of a part, just 7.66 divided by 85. So it's a really small contribution to the thing. It's almost entirely because of the bending. And even then, when we try to find what the equivalent, when we get rid of the mid-range component, which is essentially what we're doing when we're finding the reversible stress, it's not even changing much. It went from 60.2 to 66.16. So anyway, we find that F from the ultimate strength from the figure 618, and we plot those into A and B. And now we're able to put this equivalent stress into this equation for the SN diagram. And that shows that we're going to predict of 22,000 cycles. Now remember that I picked just for comparison to power, 1600 RPM. In that case, if that would last 1.4 minutes. Now, you can't possibly expect to have be able to time this to that accuracy onto the thing. So here's where that lands on this graph right here. The load line, you can see, is so much more alternating than it is mid-range. And you could also see our purple line where it is just coming up to there, right? So it's making that to like 66, right? So increase it from like 60.2 or something like that to 66 right up in here. Yeah, boom, right there. And then you can see right there on our SN diagram, we're getting really to near the low cycle fatigue breakoff point, right in there, our 2,000 cycles. I had some excerpts from the FE book just to try to show where this stuff is relevant, or the stuff that we've been covering, where it is in the equation book for the Fundamentals of Engineering exam from NECES, NCEES. You can go look it up yourself from NECES. So we don't really talk about the Coulomb-Moore theory kind of idea, but the idea is that you could have, if you have a material that has a tension and compression strength that are different from each other, you could plot the Moore's circle on top of, superimpose them on there, and then you would note that there's be this line and this kind of cone that this encapsulates. Just it's a graphical way of explaining the same thing that we were doing when we did the brittle Coulomb-Moore. So, but this is just the general Coulomb-Moore, not necessarily brittle, but it's just addressing those things. But we have learned in our 3D Moore circle this content, the maximum normal stress theory. This is not the theory that we will follow, because this one creates a box, and we found that just a straight box doesn't work, right? So here it is right here. This would be that kind of brittle Coulomb-Moore or Coulomb-Moore idea, right? That we're comparing ultimate strength to the tension, and the one in tension, we're comparing those. And when it comes to compression, which would be sigma 3, would be the most compressive of them, we're comparing the apples to apples right here.
and there's the negative to cancel out the compressive. And we're just saying that it's got to be greater than or equal to 1. But then if we usually replace that 1 with a 1 over the safety factor. So that's where the safety factor equation comes. But anyway, maximum shear stress theory, we've talked about that. So that's why I'm highlighting it. And we're really comparing tau max, absolute maximum shear stress, which is sigma 1 minus sigma 3 over 2, right? That's really the radius of the big more circle, and we're comparing that to 1/2 of the yield strength. So there you go. That's where we've covered the maximum shear stress theory. It was covered in this equation, but they didn't actually write it out. Distortion energy theory, right here, this is where von Mises comes from, and you can see our von Mises equations as we've been using them, and they appear in this equation book. So there you go. That's why one of the reasons, some of the rationale where, well, we got to cover that in this course. Here's some, okay, so for variable loading, that was us. That's our fatigue right now. You see we got modified Goodman, and so right here he is. There's our Goodman criteria. And then there's also Soderberg right there. So Soderberg, but you can see they don't cover any of the others. These are the only 2 ones that are included in the equation book. And you might say, well, that's some amount of rationale that that should be the limit of what we cover. I'm just saying from one perspective, not necessarily is that 100% true. All right, so we also do the endurance limits for steels, the SE. You can see we do the same thing with the KA, KB, KC, KD, KE. They leave out KF, and they have, this looks like it's from the 10th edition. They're using the 10th edition surface factor numbers, and here's for KB, right, for these diameters, and having an effective diameter they're putting into there, and then load factors. A little bit different. They have a little axial loading for this right here. So they have a little difference between what we've been doing. Interesting. And they're using, for torsion, they're using 0.577 instead of 0.59. Interesting. They don't give you anything about the temperature factor. Nothing. And this is miscellaneous effects. Their KE is miscellaneous effects compared to ours. Anyway, I just thought I would put in what that book has to say about the things that we cover. And so we're done.